Hello there, and welcome back to the Science Sleepy Minds. You're floating in the darkness of space right now, somewhere impossibly far from home, staring at something that shouldn't exist. It's not a star, it's not a galaxy, it's a hole in reality itself, a black hole so preposterously massive that if you could somehow place it where our sun sits, its edge would stretch past Neptune, past Pluto, past even the distant Kuiper belt where lonely ice chunks tumble in the dark. This is TON 618, and you probably won't survive learning about it. Not because the knowledge is dangerous, but because your brain might just give up trying to process numbers this absurd. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you're watching from and what time it is for you right now. I love seeing how this little corner of YouTube connects sleepy minds across time zones. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. TON 618 isn't just big, it's cosmically, hilariously, almost offensively big. We're talking about a black hole with a mass of roughly 66 billion times that of our Sun. 66 billion. That's not a typo. That's not me accidentally adding zeros while half asleep at my keyboard. That's the actual estimate, and it makes TON 618 one of the most massive black holes we've ever detected in the observable universe. To put that in perspective, our own Milky Way galaxy's central black hole, Sagittarius A star, weighs in at about 4 million solar masses. TON 618 could swallow 16,000 Sagittarius A stars and still have room for dessert. But mass is just the beginning of this cosmic horror show. What really scrambles your sense of scale is the event horizon, that point of no return beyond which nothing, not even light, can escape. For TON 618, that boundary stretches approximately 1,300 astronomical units across. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Neptune orbits at 30 astronomical units. The Voyager 1 spacecraft, humanity's most distant ambassador, is currently about 160 astronomical units away, after travelling for more than 4 decades. TON 618's event horizon is so vast that you could fit multiple copies of our entire solar system inside it, with room to spare between them. It's the kind of scale that makes you feel less like a tiny human and more like a confused bacterium trying to understand the ocean. And here's the thing that'll really keep you up at night, or rather, help you drift off into uneasy cosmic dreams. TON 618 is so far away that when we look at it, we're seeing light that left when the universe was less than 1 billion years old. It's been travelling for over 10 billion years to reach our telescopes. This monster black hole existed when the cosmos was still in its awkward teenage phase, and somehow it had already grown to this incomprehensible size. How does something accumulate 66 billion suns worth of matter in such a relatively short cosmic time span? Astronomers still argue whether we fully understand the feeding mechanisms that could bulk up a black hole this quickly. You might be wondering how we even know this thing exists. After all, black holes are by definition black. They don't emit light. They're essentially cosmic sensors, hiding everything behind an impenetrable veil of warped space-time. But TON 618 gives itself away by being an absolute glutton. It's actively feeding, pulling in vast amounts of gas and dust that form a swirling accretion disk around it. As this material spirals inward, friction heats it to millions of degrees, and it radiates energy across the electromagnetic spectrum. Radio waves, visible light, X-rays, the whole cosmic menu. This makes TON 618 what astronomers call a quasar, one of the brightest objects in the universe. It's so luminous that despite being over 10 billion light-years away, we can still detect it with Earth-based telescopes. The irony's perfect. the darkest objects in the universe reveal themselves by being surrounded by some of the brightest light imaginable. What's particularly amusing, in a deeply unsettling way, is that if you could somehow watch TON 618 from a safe distance, and let me be clear, there is no safe distance that wouldn't require you to be in another galaxy entirely. You wouldn't see a neat little black circle against space. You'd see a blazing disk of tortured matter screaming its last electromagnetic goodbyes before plunging past the event horizon forever. You'd see jets of particles shooting out from the poles at nearly the speed of light, powered by magnetic fields wound tight by the spinning disk. It would be simultaneously the most beautiful and most terrifying sight in creation, like watching a cosmic wood chipper designed by a committee of supernovae. You need to understand what you're actually looking at when you picture a black hole, because despite decades of science fiction getting it mostly wrong, these objects are stranger than any Hollywood director dared to imagine. At its most basic, a black hole is what happens when gravity wins completely and absolutely. Take enough mass, compress it into a small enough space, and space-time itself breaks. Well, not breaks exactly. Einstein's equations hold up just fine, thank you very much, but curve so severely that it creates a region from which nothing can escape. Let's start with the event horizon, because that's the boundary that defines the black hole's size, even though there's not really a physical surface there. Cross that invisible line and you're done. Finished. Game over. Every possible path forward through space-time, every conceivable trajectory you could take, leads inward toward the center. You can't turn around. You can't fire your rockets and fight your way back out. It's not a matter of needing more powerful engines or better technology. The universe's fundamental geometry has changed such that out doesn't exist as a direction anymore. Up, down, left, right, forward, backward, they all point toward the singularity at the center. It's like being trapped in a hallway where every door, including the one you just came through, now leads to the same room. The singularity itself is where things get properly weird. According to general relativity, all that infalling mass gets compressed to a point of infinite density, a mathematical impossibility that physicists know represents the breakdown of our theories rather than something physically real. We think. Honestly, nobody knows what happens at the singularity because the extreme conditions break the equations we use to describe reality. It's the universe's way of hanging up an out-of-order sign. Some theories propose that quantum effects we don't yet understand prevent true infinities. Others suggest that the singularity might be a gateway to another universe, though that's the kind of speculation that gets you eye rolls at astronomy conferences unless you've got the math to back it up. Here's something that'll twist your brain. The event horizon isn't actually a special place from the perspective of someone falling in. If you were somehow approaching a supermassive black hole like TON 618, and we'll ignore for now the various ways the universe would kill you long before you got there, you wouldn't notice anything particularly dramatic as you crossed that boundary. No warning signs, no cosmic abandon hope message carved in burning letters. Space wouldn't suddenly turn black or feel different. You'd just cross an invisible line in space-time and continue falling, completely unaware that you'd just passed the point of no return. Meanwhile, anyone watching you from outside would see you slow down and freeze at the event horizon, your image red-shifting and dimming until you faded from view. You'd see the entire future history of the universe play out in fast-forward above you, though you wouldn't live long enough to appreciate the show. Time dilation is a hell of a drug. Black holes come in different mass categories, and understanding where TON 618 fits helps grasp its absurdity. Stellar mass black holes form when massive stars explode in supernovae, typically weighing between 5 and 100 times the Sun's mass. These are the small ones, relatively speaking. Then you've got intermediate mass black holes, a somewhat mysterious category ranging from hundreds to thousands of solar masses. We've found candidates, but the census is still ongoing. And then there are the supermassive black holes. The category TON 618 dominates like a heavyweight champion who accidentally wandered into a children's boxing match. These monsters lurk at the centres of galaxies and range from millions to billions of solar masses. Historians still argue whether supermassive black holes formed first and galaxies coalesced around them, or if galaxies formed first and their central black holes grew over time by feeding and mergers. One delightfully quirky fact about black holes: they have no memory of what fell into them beyond mass, charge and angular momentum. This is called the no-hair theorem, a name that sounds like it was coined by physicists having too much fun at a conference, and that's exactly what happened. A black hole made entirely of hydrogen atoms is indistinguishable from one made of old spacecraft, former stars, or an entire alien civilization's worth of Wikipedia articles. All the information about what went in appears to be lost, which bothers physicists tremendously, because quantum mechanics insists information can't actually be destroyed. This is the famous black hole information paradox, and Stephen Hawking spent decades wrestling with it. Picture yourself as an astronomer in the 1970s, back when computers filled entire rooms and processed data slower than your phone loads cat videos today. You're part of a team conducting a radio survey of the sky, cataloguing distant objects that emit radio waves. Most of what you find is fairly mundane by cosmic standards: pulsars, radio galaxies, the usual suspects. Then you stumble across something designated TON 618, named after the Tonnant-Zintler Observatory catalogue. It's a quasar, meaning it's a quasi-stellar radio source, an object that looks almost like a star in optical photographs but radiates enormous amounts of energy across multiple wavelengths. And this one is particularly bright, which immediately tells you something interesting is happening over 10 billion light-years away. The discovery wasn't dramatic in the Hollywood sense. No alarms went off, no scientist dramatically threw down their coffee cup while shouting, "Eureka!" Science rarely works that way, despite what movies would have you believe. Instead, TON 618 was methodically catalogued, its properties measured, its spectrum analysed. Astronomers noted its high redshift, indicating it was extraordinarily distant, and thus we were seeing it as it existed when the universe was young. They calculated its luminosity and realised this object was pumping out energy, equivalent to what you'd get if you converted the mass of several hundred stars into pure radiation every year. Something was feeding a cosmic furnace on a scale that beggared imagination. What makes the discovery particularly fascinating is that this was all happening during a golden age of quasar research. Astronomers had only recently figured out what quasars actually were, not weird stars in our own galaxy, but supermassive black holes in the centres of distant galaxies surrounded by blazing accretion disks. The theory that supermassive black holes powered quasars had been proposed in the 1960s by figures like Donald Lyndon Bell and others, but it took observational evidence to convince the skeptics. Each new quasar discovery added another data point, another piece of the puzzle showing that these objects represented a common phase in galaxy evolution rather than exotic outliers. TON 618 stood out even among its quasar cousins because of its sheer luminosity. The brightness you observe from a quasar tells you about the rate at which matter is falling into the central black hole. More food equals more light from the friction-heated accretion disk. For TON 618 to shine as brightly as it does from such an incredible distance meant the black hole had to be absolutely massive, feeding on a scale that made other supermassive black holes look like they were on a diet. Historians still argue whether early astronomers fully grasped just how massive TON 618 would turn out to be once better measurement techniques came along, or if they suspected they'd found something truly exceptional even with their limited data. Here's a quirky bit of astronomical detective work. Figuring out the distance to TON 618 relies on measuring its redshift, which tells you how much the universe has expanded since the light left the object. Light gets stretched to longer, redder wavelengths as space itself expands. It's like drawing dots on a balloon and then inflating it, watching the dots move apart. TON 618 has a redshift value of about 2.219, which, using our current understanding of cosmic expansion, puts it roughly 10.8 billion light-years away. That means the light we're seeing today began its journey when the universe was only about 3 billion years old, still in its cosmic childhood compared to its current age of 13.8 billion years. The early observations raised immediate questions that astronomers are still working to answer fully. How did a black hole accumulate so much mass so quickly after the Big Bang? The universe at 3 billion years old was still relatively young, without the billions of years of star formation, death and galaxy mergers we see in the later cosmos. For TON 618 to already weigh 66 billion solar masses required extraordinarily efficient feeding mechanisms or perhaps special conditions in the early universe that we're only now beginning to understand. Some models suggest that the first black holes might have formed from massive primordial gas clouds that collapsed directly, skipping the star phase entirely. These seed black holes could have been born with hundreds or thousands of solar masses already in the bank, giving them a head start on their long journey to becoming monsters like TON 618. Now comes the truly brain-melting part. How do you weigh something that's invisible, surrounded by glowing chaos, and sitting more than 10 billion light-years away? You can't exactly roll it onto a cosmic bathroom scale. Instead, astronomers use the black hole's effects on its surroundings, reading the signatures of gravity written in light and motion. The primary method involves analysing the quasar's luminosity and applying what's called the Eddington limit. This limit describes the maximum brightness a black hole of a given mass can achieve through accretion before its own radiation pressure starts pushing away the infalling material. Think of it as a cosmic speed limit for eating. Shove food in too fast and some of it bounces back. For TON 618, astronomers observed its staggering brightness and worked backward. If the black hole is shining this brightly, and we assume it's feeding at or near the Eddington limit, then solving the equations gives you a minimum mass estimate. The math spits out a number that makes you double-check your calculator. Approximately 66 billion solar masses, give or take a few billion. The uncertainty bars on that measurement are enormous, but even the conservative estimates put TON 618 firmly in the incomprehensibly massive category. Another technique involves studying the motion of gas in the accretion disk using spectroscopy. When gas orbits a massive object, some of it moves toward us and some away, causing Doppler shifts in the emission lines, the same effect that makes ambulance sirens change pitch as they pass. By measuring how fast material orbits at different distances from the black hole, you can apply Kepler's laws of orbital motion to calculate the mass of the central object. For TON 618, the material orbiting close to the event horizon is screaming around at significant fractions of the speed of light, its spectral lines smeared by both Doppler effects and gravitational redshift. Unpacking all those overlapping effects requires sophisticated modelling, but the results consistently point to a preposterously massive central black hole. Gravitational lensing provides yet another measurement tool, though it's trickier to apply to objects as distant as TON 618. When light from a background object passes near a massive foreground object, the foreground object's gravity bends space-time and acts as a lens, distorting and magnifying the background light. In principle, analysing these lensing effects tells you about the mass distribution doing the bending. For TON 618, any lensing measurements are complicated by the fact that the quasar itself is so bright it tends to drown out fainter background objects. Still, combining multiple measurement techniques helps astronomers triangulate more accurate mass estimates and understand the uncertainties in their calculations. Here's where it gets delightfully uncertain. Different measurement methods sometimes give slightly different answers, and the error bars on measurements of distant objects can be substantial. Some estimates for Ton 618's mass go as high as 66 billion solar masses, while others suggest it might be only 40 billion or so. In astronomy, when you're talking about numbers this large, being off by 20 billion solar masses still leaves you with the same fundamental conclusion. This thing is cosmically huge. Historians still argue whether future observations with more sensitive instruments will significantly revise these mass estimates or confirm that Ton 618 truly is one of the heavyweight champions of the universe. A quirky aspect of these measurements involves understanding the black hole's spin. Black holes can rotate, and a spinning black hole drags space-time around with it in a process called frame dragging. This affects the inner edge of the accretion disk and the efficiency of converting matter into radiation. A maximally spinning black hole can extract more energy from infalling material and thus shine more brightly for the same accretion rate. For TON 618, figuring out whether it's spinning rapidly or relatively slowly helps refine the mass estimate. But measuring the spin of a black hole billions of light years away pushes current observational techniques to their limits. Let's bring this cosmic horror show home by comparing Ton 618 to the supermassive black hole in our own galactic backyard. At the heart of the Milky Way, about 26,000 light-years from Earth toward the constellation Sagittarius, lurks Sagittarius A star, SGR A star for short, pronounced Sagittarius A star, though most astronomers just say Sag A star because we're all too tired to pronounce the full name properly after a long observing night. SGR A star weighs roughly 4.3 million solar masses. In the context of supermassive black holes, this is actually quite modest, almost dainty. Our galaxy's central black hole is what you might call a middleweight, substantial enough to gravitationally dominate the galactic core but nowhere near the upper end of the mass spectrum. For comparison, the Andromeda Galaxy's central black hole masses somewhere around 140 million solar masses, roughly 30 times heftier than ours. And then there's Ton 618, outweighing Sirius star by a factor of more than 15,000. If Sirius star is a house cat, Ton 618 is a blue whale. Actually, that analogy doesn't do it justice. If Sagittarius A star is a grain of sand, TON 618 is a small car. The scale difference is just absurd. The event horizon size comparison really drives the point home. SGR A star's event horizon has a diameter of about 24 million kilometers, or roughly 17 solar diameters. You could fit the orbit of Mercury inside it with room to spare, but you definitely couldn't fit Earth's orbit. It's impressively large by everyday standards, but compact on solar system scales. Now remember that Ton 618's event horizon stretches 1,300 astronomical units. That's roughly 40 times farther than Neptune orbits from our Sun. If you replaced our Sun with SGR A star, the Earth would survive outside its event horizon, our orbit intact though deeply confused about the sudden absence of sunlight. If you replaced our Sun with Ton 618, not only would Earth be swallowed instantly, but the event horizon would extend well past the Kuiper belt, past where the solar wind peters out, past where Voyager 1 is currently wandering. Our entire solar system would be a tiny snack disappearing into an enormous cosmic maw. Here's a fun thought experiment that'll make you feel appropriately insignificant. If Ton 618 somehow materialized where our Sun currently sits, ignoring for a moment that this would violate several fundamental laws of physics and probably unravel the fabric of space-time in creative ways, the gravitational effects would be felt immediately across the entire solar system. The planets wouldn't orbit in neat ellipses anymore. Everything would start falling inward, trajectories transforming into death spirals. Earth would have about 8 minutes before the gravitational changes propagated to us at light speed, and then our orbit would begin decaying. We'd spiral in over a period of time that would depend on complex gravitational calculations. I'm too sleepy to work out right now, but the end result would be inevitable. Into the maw we'd go, spaghettified and vaporized long before we reached the event horizon. Astronomers still argue whether the mass ratio between galactic black holes and their host galaxies follows a universal pattern. For a long time, observation suggested that supermassive black holes typically make up about 0.1% of their galaxy's bulge mass, the dense central region of stars. Our Milky Way roughly fits this relationship, but TON 618 seems to be an outlier, residing in a galaxy whose total mass likely doesn't scale up as dramatically as the black hole's mass did. It's like finding a heart 3 times larger than the person it belongs to. Functional, perhaps, but definitely unusual. This discrepancy hints that TON 618 might have grown through unusual means, perhaps gobbling up multiple smaller black holes during galaxy mergers, or it might represent a brief phase when the black hole temporarily outpaced its galaxy's growth. One quirky detail about Sagittarius A star: we've actually imaged it. In 2022, the Event Horizon Telescope collaboration released the first direct image of our galactic centre's black hole, showing the shadow cast by the event horizon against the glowing accretion disk. It was a monumental achievement requiring coordinating radio telescopes across the globe to create an Earth-sized virtual telescope. Imaging TON 618 in similar detail remains far beyond our current capabilities. It's simply too distant and too small in angular size despite its enormous actual size. We see its effects, its blazing quasar glow, but the black hole itself remains a mathematical inference rather than a direct observation. The event horizon of TON 618 deserves its own meditation because the numbers involved are so preposterous, they almost lose meaning. 1,300 astronomical units. Let's unpack that properly, so your sleepy brain can really marinate in the cosmic horror of it all. 1 astronomical unit, as you probably remember from earlier, is the average distance from Earth to the Sun, about 93 million miles, or 150 million kilometers if you prefer metric. It's the distance sunlight travels in 8 minutes and 20 seconds, the space you'd need to cross to high-five our home star, assuming you didn't vaporize the instant you got within a few million kilometers. Neptune, the outermost proper planet in our solar system, orbits at 30 astronomical units from the Sun. It takes sunlight about 4 hours to reach Neptune, and it took Voyager 212 years to get there from Earth, using gravitational assists from the other planets. Now multiply that Neptune distance by 43. That's how far TON 618's event horizon extends in radius. The diameter, the distance straight across, would be 2,600 astronomical units. To drive the point home with even more numerical violence, the Oort cloud, that theoretical shell of icy bodies surrounding our solar system at vast distances, is thought to extend from 2,000 to 100,000 astronomical units from the Sun. TON 618's event horizon would swallow the inner Oort cloud. The entire inner solar system, the Sun, all the planets, the asteroid belt, the Kuiper belt, the heliopause where the solar wind peters out, all of it would fit inside TON 618's event horizon multiple times over with space left between copies. You could potentially fit dozens of solar systems inside this black hole's point of no return, arranged like cosmic nesting dolls. Here's a perspective shift that makes it even stranger. Light takes about 4 hours to cross from the Sun to Neptune's orbit. Light crossing, TON 618's event horizon diameter would take roughly 3.5 days of continuous travel at the universe's speed limit. 3.5 days to cross an edge, a boundary that isn't even a physical thing, just a line in space-time where the geometry changes such that all futures lead inward. The event horizon is not a wall or a surface, There's no material there. It's pure geometry, pure gravitational inevitability. And it's so enormous that light needs days to traverse it. Historians still argue whether there's a practical upper limit to how large a black hole's event horizon can grow. In principle, if a black hole keeps feeding, its event horizon keeps expanding. The relationship is directly proportional to mass. Double the mass, double the event horizon radius. But there are practical constraints. At some point, a black hole becomes so massive and its event horizon so large that there simply isn't enough nearby matter to feed it efficiently. The radiation from the accretion disk pushes material away, and galaxy-scale gravitational dynamics become relevant. TON 618 might be approaching, or at the practical upper limit for black holes in the current universe. Though practical limit in cosmology is a squishy concept since we're talking about timescales of billions of years. One delightfully quirky consequence of having such a large event horizon: the tidal forces at the edge are actually weaker than for smaller black holes. Tidal forces, the stretching effect that causes spaghettification, depend on the gradient of the gravitational field, how quickly gravity changes over a distance. For a stellar mass black hole a few miles across, the gravitational difference between your head and feet as you approach the event horizon would be extreme enough to tear you apart well before you cross the boundary. But TON 618's event horizon is so vast that the gravitational gradient near it is actually relatively gentle. You could theoretically cross the event horizon of a supermassive black hole like TON 618 and remain intact, at least for a little while, before tidal forces deeper inside eventually shredded you. Not that this is comforting. You're still doomed once you cross, but it's a fascinating consequence of scale. The bigger the black hole, the more survivable the initial approach, right up until it's very suddenly not survivable at all. The event horizon also serves as a one-way membrane for information. Anything that crosses it, particles, light, information, your ill-advised spacecraft, is gone from the perspective of the outside universe. You leave no trace except adding an infinitesimal amount to the black hole's mass. This makes black holes the universe's ultimate data shredders, which, as mentioned earlier, bothers physicists who believe information should be conserved. The resolution to this paradox might involve quantum effects at the event horizon that are currently beyond our ability to calculate or observe, but that's a puzzle for Section 17 to explore once you're even sleepier than you are now. Quasars are what happen when supermassive black holes stop being polite and start getting real. They're the brightest sustained objects in the universe, beacons visible across billions of light years, and they're all powered by black holes in the throes of cosmic gluttony. TON 618 is a quasar, which means it's not just sitting quietly in space like SGR A star mostly does. It's actively feeding, pulling in vast amounts of matter, and converting gravitational potential energy into radiation with terrifying efficiency. The name quasar is a contraction of quasi-stellar radio source, coined back when astronomers first discovered these objects and weren't quite sure what they were looking at. They appeared star-like in photographs, single points of light rather than extended objects, but they radiated enormous amounts of energy and had peculiar spectra that didn't match any known stars. The breakthrough came when astronomers realized these objects had extraordinarily high redshifts, placing them at cosmological distances. Something in the early universe was producing the luminosity of 100 galaxies from a region smaller than a solar system. That kind of power density could only come from one source: matter falling into a supermassive black hole. Here's how the quasar engine works in practice. A supermassive black hole sits at the center of a galaxy, and matter from the surrounding environment, gas clouds, shredded stars, cosmic dust, whatever's available, begins falling toward it. But matter doesn't fall straight in. Everything has some angular momentum, some sideways motion, So instead of plunging directly into the black hole, the infalling material settles into an accretion disk, a swirling maelstrom of gas and dust gradually spiraling inward. This is where the magic happens, if by magic you mean violent physics that would absolutely kill you. As material in the accretion disk spirals inward, friction between adjacent layers heats it up, and we're not talking about campfire temperatures here. The inner regions of the accretion disk, just outside the event horizon, reach temperatures of millions or even billions of degrees. At those temperatures, atoms are completely ionized, and the gas emits radiation across the entire electromagnetic spectrum. The brightest emission typically peaks in the ultraviolet and X-ray portions of the spectrum, though there's plenty of visible light too. This is why quasars shine so brightly. They're essentially cosmic furnaces powered by gravity, converting the mass of infalling matter into radiation with an efficiency that makes nuclear fusion look quaint. Matter falling into a black hole can convert up to 40% of its mass into energy via this process, compared to fusion's measly 0.7%. TON 618's quasar phase means it's currently feasting. Astronomers estimate that to maintain its observed luminosity, TON 618 must be accreting matter at a rate of hundreds of solar masses per year. That's an almost incomprehensible amount of material, the equivalent of devouring an entire star's worth of mass every few days. Where does all this food come from? Likely from the surrounding galaxy. Dense gas clouds in the galactic core, stars that wandered too close and got shredded by tidal forces, smaller satellite galaxies that merged with the host galaxy and dumped their contents toward the center. Galaxy mergers are particularly efficient at funneling matter towards central black holes, which is why quasars were more common in the early universe when galaxy mergers were happening more frequently. Historians still argue whether all supermassive black holes go through quasar phases, or if only certain galaxies under specific conditions produce them. The current thinking is that most supermassive black holes probably had active quasar phases in their past, when their host galaxies were younger and gas-rich. Our own Sagittarius A star might have been a quasar billions of years ago, blazing away before it exhausted the easily accessible gas supply in the Milky Way's core. Now it's relatively quiet, only occasionally snacking on a wayward gas cloud or unlucky star. TON 618, being observed as it was in the early universe, catches the black hole during its feast years, like photographing a teenager at the height of their inexplicable ability to eat an entire pizza and still be hungry an hour later. One quirky aspect of quasars: they tend to be surrounded by clouds of ionized gas extending for thousands of light years, illuminated by the intense radiation from the central engine. These regions are called emission line regions because they show characteristic spectral lines from ionized hydrogen, oxygen, and other elements. Studying these regions tells astronomers about the chemistry of the early universe and helps us understand how quasars affect their surroundings, a topic we'll return to when discussing galaxy evolution. The accretion disk around TON 618 is where the universe throws a physics party, and everyone's invited except you, because you'd be vaporized instantly. This disk is not a neat, orderly structure like Saturn's rings photographed in pretty pastels. It's a churning hellscape of superheated plasma, twisted magnetic fields, and radiation intense enough to sterilize anything for light years around. Welcome to nature's most violent blender. Picture a spiral of gas and dust extending outward from the event horizon for potentially thousands of astronomical units, though the brightest and hottest regions are concentrated much closer in. The material in this disk isn't orbiting sedately. It's screaming around the black hole at significant fractions of light speed, the inner regions whipping past in orbital periods measured in minutes or hours rather than years. At these speeds, relativistic effects become significant. Time dilation, length contraction, beaming of radiation in the direction of motion, all the weird consequences of Einstein's relativity are cranked up to maximum. Friction between layers of the disk generates the heat, but friction is perhaps too gentle a word for what's actually happening. Imagine turbulent vortices in the plasma, magnetic field lines tangled and snapping, particles accelerating to near-light speed in the chaos. The disk's inner edge, just outside the innermost stable circular orbit, the last place matter can theoretically orbit before plunging into the event horizon, reaches temperatures exceeding billions of degrees. At these temperatures, the plasma emits primarily in X-rays, which is why X-ray telescopes are so crucial for studying black hole accretion. The radiation pressure from this inferno is so intense, it can actually blow away incoming material, creating winds and outflows that carry matter back out into the galaxy at velocities of thousands of kilometers per second. But wait, there's more cosmic violence to consider. Perpendicular to the accretion disk, many quasars, including TON 618, produce relativistic jets, narrow beams of particles and radiation shooting out from near the black hole's poles at speeds approaching the speed of light. These jets can extend for millions of light-years into intergalactic space, making them some of the largest structures associated with single objects in the universe. The mechanism producing the jets involves the black hole's spin and the magnetic fields threading through the accretion disk, though the exact details are still being worked out. Essentially, the magnetic fields act like a particle accelerator, channeling energy and matter into tight beams and flinging them outward. If one of these jets happened to point directly at Earth, we'd detect the quasar as a blazar, an even more dramatic subclass of active galactic nucleus. The amount of energy pouring off TON 618's accretion disk is difficult to comprehend in human terms. The quasar shines with a luminosity equivalent to roughly 140 trillion suns. 140 trillion. If you could somehow capture all that energy, which you can't, but let's pretend, you could power human civilization at current usage rates for longer than the universe has existed, multiple times over, and barely make a dent in the output. And this energy is just the waste heat from matter spiraling into a black hole. It's not even the primary function, it's the exhaust. Historians still argue whether accretion disks around supermassive black holes are smooth structures or clumpy, whether they're thick and puffy or thin and pancake-like. Observation suggests the answer is it depends, and probably all of the above at different radii. The outer regions of an accretion disk can be relatively cool and geometrically thick, perhaps resembling a dusty torus that obscures the central engine from certain viewing angles. The middle regions form the hot, thin disk where most of the visible light and UV radiation is generated, and the innermost region, the so-called corona, is a zone of extremely hot plasma hovering above and below the disk, generating the X-ray emission through inverse Compton scattering and other exotic processes that sound like they belong in a science fiction novel, but are actually just plasma physics being its usual dramatic self. One quirky detail about accretion disks: they can be unstable. Sometimes the accretion rate isn't constant but varies over time, leading to flares and dimming in the quasar's brightness. For TON 618, being observed as a snapshot from billions of years ago, we're seeing it in whatever state it happened to be when that light departed. Other quasars show variability over timescales ranging from hours to years, telling us about the dynamics of matter swirling around their central black holes. Time near TON 618 doesn't work the way your sleepy brain thinks it does, and this is where general relativity starts to feel less like physics and more like cosmic horror, written by a mathematician with a zadistic streak. Massive objects curve space-time, and black holes curve it so severely that time itself becomes negotiable. relative, entirely dependent on where you're standing and how fast you're moving. Let's say you're in a spacecraft hovering at a safe distance from TON 618's event horizon, maybe a few thousand astronomical units out, far enough that the tidal forces aren't a concern but close enough that gravitational time dilation is measurable. You have a clock with you, a precise atomic clock ticking away the seconds. Back on Earth, or wherever your home base is, your colleagues also have an identical atomic clock. According to general relativity, your clock near the black hole runs slower than the clock far from the black hole. Not because your clock is broken, but because time itself is flowing at different rates in the two locations. The math comes from the Schwarzschild metric, the solution to Einstein's field equations for a non-rotating black hole. For a more realistic rotating black hole, you'd use the Kerr metric, but the basic principle is the same. The closer you get to the event horizon, the slower time flows relative to a distant observer. At the event horizon itself, time dilation becomes infinite from an outside perspective. A clock crossing the event horizon appears to freeze, ticking slower and slower, asymptotically approaching zero as it crosses the boundary. Meanwhile, from the perspective of someone falling in, their clock ticks normally, and they cross the event horizon in finite time, blissfully unaware that to everyone else they appear frozen at the edge forever. For TON 618 specifically, the time dilation effects near but outside the event horizon would be extreme but not as dramatic as for smaller black holes until you got very close. Remember, the event horizon for this monster extends 1,300 astronomical units. If you're hovering 100 astronomical units outside the event horizon, still well within the black hole's gravitational influence, the time dilation would be noticeable but not overwhelming. Let's say your clock runs at 99% the rate of a distant clock. Over the course of a year by your clock, about 1 year and 4 days would pass for the distant observer. Annoying if you're trying to coordinate schedules, but not the dramatic interstellar movie scenario where you come back to find everyone you knew has aged decades. But get closer, say 10 astronomical units from the event horizon, and the effects become severe. Your clock might now run at only 50% the rate of a distant clock. Spend 1 year near the black hole, and 2 years pass in the outside universe. Closer still, 1 astronomical unit from the event horizon, and time dilation could mean one of your years equals 10 or 100 years far from the black hole. The relationship is non-linear. Time dilation accelerates rapidly as you approach the event horizon, approaching infinity at the boundary itself. This has bizarre consequences for communication. Imagine you're part of a mission exploring near TON 618, with one team hovering at a safe distance and another team, let's call them the expendable curious ones, venturing closer to the event horizon. The close team sends regular radio updates, 1 transmission every hour by their clock. The distant team receives these transmissions increasingly spaced out as the close team descends. 1 hour between signals becomes 2 hours, then 4, then 8. Eventually the signals are arriving days apart, then weeks, then longer. If the close team actually crosses the event horizon, their final transmission would be redshifted and time dilated such that it technically never quite arrives. It asymptotically approaches the distant team over infinite time, fading into undetectable noise long before then. Historians still argue whether anything can actually survive close enough to a supermassive black hole like TON 618 to experience extreme time dilation without being destroyed by other effects first. Radiation from the accretion disk would sterilize and then vaporize any spacecraft long before you got close enough for time dilation to become the primary concern. But in theory, if you could shield yourself from the radiation and tidal forces, you could park yourself in a region of significant time dilation and essentially time travel into the future. Park yourself where one of your years equals 10 years in the outside universe, wait what feels like a year, then return home to find a decade has passed. This is the only form of time travel relativity permits. Forward only, no returns, no paradoxes. One quirky implication: if you fell into TON 618, from your perspective the journey from event horizon to singularity would take a finite, calculable amount of time, probably a few hours for a black hole this massive. But from the outside universe's perspective, you'd never quite cross the event horizon. Your image would freeze there, redshifted and dimmed forever. Both perspectives are equally valid in relativity. You cross in finite proper time, but the universe never sees you cross. This is why black holes have been described as frozen stars. Their event horizons are carpeted with the eternally falling, time-frozen images of everything that ever fell in, at least in principle. Spaghettification is the technical term astrophysicists use when they want to sound professional, while describing how a black hole turns you into noodles. The formal term is tidal disruption. But let's be honest, spaghettification is infinitely more memorable and accurately conveys the fundamental horror of being stretched into a very long, very thin version of yourself before being ripped apart at the atomic level. Here's how it works. Gravity follows an inverse square law, meaning its strength drops off with a square of distance. Double your distance from a mass, and the gravitational pull drops to 1/4. This seems reasonable enough when you're standing on Earth's surface, where the difference in gravity between your head and feet is negligible because you're small compared to Earth's radius. But near a black hole, the gravitational gradient, the rate at which gravity changes over distance, becomes severe enough that the difference matters a lot. Imagine you're falling feet first toward a black hole. Your feet are closer to the singularity than your head, so they experience stronger gravitational pull. The difference might be small at first, but as you get closer to the event horizon, the gradient increases. Soon your feet are being pulled noticeably harder than your head, stretching you vertically. At the same time, the gravitational field is pulling everything toward the center of the black hole, which squeezes you horizontally as both sides of your body are pulled toward the midline. Stretched vertically, compressed horizontally, you're being turned into a human strand of spaghetti, hence the name. For a stellar mass black hole, say 10 solar masses, the event horizon is only about 60 kilometers across. The tidal forces near such a small black hole are catastrophically strong even well outside the event horizon. You'd be spaghettified long before crossing the point of no return, torn apart while still technically able to escape if someone could somehow pull you back up the gravity well. Your death would at least have the dignity of being technically survivable if you'd just not gotten so close. Not that this is comforting. But TON 618 presents a different scenario. Remember, its event horizon is 1300 astronomical units across. The tidal forces at the event horizon itself are much weaker than for smaller black holes, because the curvature of space-time is less extreme over human-scale distances. You could theoretically cross TON 618's event horizon intact, completely whole, without any stretching. For a brief moment, you'd experience the surreal sensation of falling through an invisible boundary, knowing you'd just sealed your fate but not feeling any different. The accretion disk's radiation would have killed you long before this point in any realistic scenario, but we're ignoring that for the sake of argument. After crossing the event horizon, you'd continue falling inward. The singularity in a Schwarzschild black hole sits at the center, zero distance from all points on the event horizon, as space-time geometry gets properly weird. In a Kerr black hole, which more realistically describes rotating black holes like TON 618, the singularity might be a ring rather than a point, though the distinction probably won't matter much to you as you approach it. As you fall deeper inside the event horizon, the tidal forces increase. What was a gentle gradient at the event horizon strengthens with every kilometer inward. Eventually, the stretching becomes noticeable, then painful, then fatal. The exact point where you'd be ripped apart depends on your structural strength and the black hole's mass. But for TON 618, you might survive for hours after crossing the event horizon before tidal forces finally shredded you. During this time, you'd have a unique perspective on the universe. Looking outward toward the event horizon, you'd see the entire future history of the outside universe playing out in fast forward due to time dilation effects. Looking inward toward the singularity, well, nobody knows what you'd see because the physics breaks down. Perhaps you'd see nothing. Perhaps you'd see everything. Perhaps the question doesn't even make sense in the geometry of space-time inside an event horizon. Historians still argue whether quantum effects might prevent spaghettification at some level, if there's a minimum scale below which tidal forces can't rip structures apart. At atomic scales, quantum mechanical effects dominate over classical gravity, and the Planck length represents a scale where space-time itself becomes quantized and our current theories stop working. But long before you reach those scales, you'd have been reduced to a plasma of ionized atoms, then to quarks and gluons, and then to whatever fundamental constituents of matter exist at energies we can't yet probe experimentally. One particularly quirky aspect: if you fell into a rotating black hole and somehow survived impossibly long, you might pass through the inner event horizon, a feature unique to Kerr black holes, and enter a region where the singularity is time-like rather than space-like, whatever that means. This is deep into the math says it's possible but probably isn't territory. Most physicists suspect that instabilities would destroy any real inner horizon, but the equations permit its existence, so we acknowledge it while side-eyeing it suspiciously. Let's conduct a thought experiment that violates several conservation laws but will help you sleep by thoroughly traumatizing your sense of cosmic security. Imagine TON 618 appears suddenly in place of our Sun. Let's not worry about how this happened. Maybe a bored Q from Star Trek decided to mess with us. The consequences would be immediate, dramatic, and absolutely apocalyptic for our solar system. First, let's address the obvious. The Sun would vanish, and with it, all the light and heat keeping Earth habitable. But the sudden darkness would be the least of our problems. See, while TON 618 masses 66 billion times more than our Sun, it's also a black hole, which means all that mass is concentrated in a much more compact form. Well, compact is relative, given the event horizon stretches 1300 astronomical units. But the point is that the gravitational field configuration would be very different from our friendly neighbourhood star. The event horizon would extend roughly 40 times Neptune's orbital distance. This means Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, Pluto, and most of the Kuiper belt would all find themselves inside the point of no return instantly. We wouldn't fall straight in. We'd still have our orbital velocity, so we'd spiral inward over time as gravitational radiation and other effects decayed our orbits. But the moment TON 618 replaced our Sun, everything in the inner solar system would be irrevocably doomed, already inside the event horizon with no possible escape. Earth's fate would be sealed in the time it takes gravitational changes to propagate at light speed, about 8 minutes for the signal to reach us. During those 8 minutes, we'd still be orbiting where the Sun used to be, completely unaware that everything had just gone catastrophically wrong. Then the gravitational wave would arrive, and Earth's orbit would suddenly be influenced by a black hole 66 billion times more massive than what we'd been orbiting a moment before. The orbital dynamics would change instantly. Our comfortable, nearly circular orbit at 1 astronomical unit would no longer be stable under the new gravitational regime. The descent wouldn't be instantaneous. We'd spiral inward over some period, hours, days, maybe weeks depending on the exact orbital mechanics, which I'll admit I'm too sleepy to calculate precisely. As we fell, the Earth would start heating up from tidal forces. Remember, even though TON 618's tidal forces at the event horizon are relatively gentle by black hole standards, we're talking about the entire planet being subjected to them. The differential gravitational pull would stress Earth's crust, triggering earthquakes and volcanic eruptions on a scale that would make the dinosaur extinction look mild. The oceans would slosh and boil, the atmosphere would heat and strip away into space. Long before we reach the event horizon, Earth would be torn apart by tidal forces, reduced to a cloud of debris spiralling toward oblivion. Jupiter and the other gas giants would suffer similar fates, though being farther out, they might last longer before being shredded. The spectacular part, if there were anyone left to watch, which there wouldn't be, would be the accretion disk forming from all this new material. The debris of 8 planets, dozens of moons, and countless asteroids and comets would spiral inward, colliding and heating up through friction. For a brief cosmic moment, the shredded remains of our solar system would form a new accretion disk around TON 618, glowing hot as gravitational potential energy converted to heat. We'd be adding an infinitesimal amount to TON 618's mass, barely enough to register given the black hole mass's 66 billion suns, and we're adding less than 1/10,000th of a solar mass worth of planetary debris. Historians still argue whether anything could orbit stably around TON 618 in the long term, given that the event horizon extends so far. In principle, yes. Anything beyond the event horizon could maintain an orbit if it had the right velocity and trajectory, but the practical reality is that any orbit close enough to TON 618 to be interesting would place you within the accretion disk's radiation field, which would be fatal. The habitable zone, if we can even call it that, would be so distant that TON 618 would provide no meaningful light or heat. You'd need your own power source, making the black hole's presence more of a hazard than a resource. One quirky detail: if you somehow had a stable viewing platform far from TON 618 and watched our solar system's destruction in fast forward, you'd see a brief fireworks show as the planets disintegrated and their remains heated up in the forming accretion disk. Then, relatively quickly on cosmic timescales, the debris would cross the event horizon and disappear. From your perspective, the material would appear to slow down and freeze at the event horizon, images red-shifting and fading. Over time, the light from the infalling matter would dim until it was undetectable, and TON 618 would return to its previous state, perhaps slightly brighter from the fresh meal but otherwise unchanged. Our entire solar system would have been erased, with barely a burp to mark its passing. Growing a black hole from stellar mass size, maybe 10 or 100 times the Sun, to supermassive proportions like TON 618 isn't something that happens overnight. We're talking about accumulating 66 billion solar masses over cosmic timescales, and the mechanisms by which this occurs are still being actively debated in astrophysics journals and at conferences where arguments get surprisingly heated, given that we're discussing events billions of years in the past. The most straightforward growth mechanism is simple accretion. The black hole pulls in nearby gas, dust, stars, and anything else gravitationally available, gradually increasing its mass. Every time matter crosses the event horizon, the black hole gets slightly heavier. But there's a catch. Remember the Eddington limit we discussed earlier? When a black hole feeds too rapidly, the radiation from its accretion disk creates outward pressure that pushes away incoming material. This self-regulating mechanism means black holes can only grow so fast through continuous feeding. The maximum growth rate through Eddington-limited accretion would take billions of years to build even a modest supermassive black hole, let alone a monster like TON 618. This is where the timeline gets problematic. TON 618 existed when the universe was only about 3 billion years old, yet it already weighed 66 billion solar masses. Starting from a stellar mass black hole seed and growing at the Eddington limit wouldn't give you enough time to accumulate that much mass. Something unusual had to be happening. Either TON 618 started from a much more massive seed than typical stellar mass black holes, or it grew through super Eddington accretion, feeding faster than the theoretical maximum by some mechanism we don't fully understand, or it grew through mergers, or some combination of all these processes. Black hole mergers are the other major growth mechanism. When two galaxies collide, and they collide fairly often in the universe's early days when everything was closer together, their central black holes eventually sink to the merged galaxy's center and coalesce into a single, larger black hole. This process efficiently adds mass without the constraints of the Eddington limit. A 1 million solar mass black hole merging with a 10 million solar mass black hole gives you an 11 million solar mass black hole instantly, plus some energy radiated away as gravitational waves. String together enough mergers over cosmic time, and you can build up supermassive black holes reasonably quickly. TON 618 likely grew through some combination of continuous feeding and mergers. The early universe was a chaotic place with frequent galaxy interactions, providing plenty of opportunities for black holes to merge and grow. Dense gas clouds in the centers of young galaxies provided abundant fuel for accretion, and if TON 618's progenitor started as an unusually massive seed black hole, perhaps forming directly from the collapse of a massive primordial gas cloud rather than from a star, it would have had a head start on accumulating mass. Historians still argue whether direct collapse black holes are common or rare in the early universe. These hypothetical objects would form when massive gas clouds, perhaps 100,000 solar masses or more, collapse directly into black holes without forming stars first. This requires special conditions: low metallicity gas without dust to cool it and fragment it into stars, strong radiation fields to keep the gas hot, specific density and temperature profiles. But if direct collapse black holes existed, they'd provide the massive seeds needed to grow giants like TON 618 in the available time. One intriguing possibility involves super Eddington accretion in thick disks. If the accretion disk is geometrically thick and puffy, radiation can get trapped in the inflowing gas and carried inward rather than pushing outward. This allows the black hole to feed faster than the classical Eddington limit would suggest. Computer simulations suggest this might happen under certain conditions, particularly in gas-rich environments in the early universe. These slim disk or thick disk models remain somewhat speculative, but provide a plausible way for black holes to grow rapidly when needed. Another factor, a GN feedback. Active galactic nuclei, quasars like TON 618, don't just grow passively. They affect their environments through radiation, winds and jets that heat surrounding gas and can actually shut down star formation in their host galaxies. This feedback mechanism may explain why we don't see even larger black holes. At some point, the black hole's activity disrupts its own food supply, limiting further growth. TON 618 might represent a brief phase where the black hole outpaced its own feedback mechanisms, growing to extreme size before the feedback caught up and choked off the fuel supply. One quirky detail about black hole growth: every time a black hole accretes matter, it technically loses mass as well through Hawking radiation, though for supermassive black holes this effect is utterly negligible. The rate of Hawking radiation is inversely proportional to the black hole's mass squared, meaning bigger black holes radiate slower. For TON 618, the Hawking radiation power is so absurdly low that it might as well be zero. The black hole gains far more mass from swallowing random cosmic rays and stray atoms than it loses through quantum evaporation. Dark matter enters this conversation not because we've observed it directly interacting with black holes. We haven't, because dark matter is frustratingly invisible to all our instruments. but because the stuff makes up about 85% of the matter in the universe, and we'd be remiss to ignore its potential role in growing supermassive black holes to monstrous sizes. You've probably heard of dark matter in the mysterious invisible stuff that holds galaxies together context. It doesn't emit, absorb, or reflect light, hence dark. It doesn't interact electromagnetically, which means it passes through normal matter like a ghost through walls. The only way we know dark matter exists is through its gravitational effects. Galaxies rotate faster than they should based on visible matter alone. Gravitational lensing reveals more mass than we can see, and the cosmic microwave background's patterns require dark matter to form structure in the early universe. Whatever dark matter is, and the leading candidates include WIMPs, weakly interacting massive particles, axions, primordial black holes, or something else entirely, it's real and it has gravity. Here's where it gets relevant to TON 618. Dark matter forms halos around galaxies, vast three-dimensional structures extending well beyond the visible galactic disk. The Milky Way sits inside a dark matter halo that probably extends hundreds of thousands of light years into intergalactic space, dwarfing the visible galaxy. These halos were likely the first structures to form after the Big Bang, with normal matter falling into the gravitational wells they created. If supermassive black holes formed early in the universe, they'd be sitting at the centres of dark matter halos, and that's where things get interesting. Some models suggest that black holes can accrete dark matter just like they accrete normal matter. Dark matter particles falling into a black hole would add to its mass, though they wouldn't form a bright accretion disk because dark matter doesn't interact electromagnetically and thus doesn't heat up through friction. This would be dark accretion, adding mass invisibly. If dark matter halos in the early universe were particularly dense, and if early black holes were efficient at capturing dark matter, this could have provided an additional mass source to help giants like TON 618 grow so large so quickly. The catch is that dark matter by its nature has very little dissipation. Normal matter can lose energy through electromagnetic radiation. Atoms collide, emit photons, lose energy, and settle into bound orbits or fall inward. Dark matter can't do this easily because it doesn't interact electromagnetically. A dark matter particle on a trajectory near a black hole might just zip past without being captured, because it can't radiate away energy to settle into an orbit or spiral inward. To capture dark matter effectively, you need mechanisms like three-body interactions where one particle's energy is transferred to another, allowing the first to be captured while the second escapes. These processes work, but they're slow. Historians still argue whether dark matter accretion is a significant contributor to supermassive black hole growth, or a minor effect compared to normal matter accretion and mergers. The truth is we don't know, largely because we don't know enough about dark matter's properties. If dark matter particles have even weak interactions with each other, or with normal matter beyond gravity, those interactions could enhance accretion rates. If dark matter forms dense spikes around black holes, a predicted phenomenon where dark matter density increases sharply near a black hole due to gravitational scattering, those spikes could provide a substantial food source. One particularly intriguing scenario involves primordial black holes as dark matter. If a fraction of dark matter consists of black holes formed in the early universe, perhaps from quantum fluctuations during inflation, then black hole mergers could have been even more common than galaxy merger rates suggest. TON 618 might have grown partially by merging with numerous smaller primordial black holes over time, hoovering up bits of the dark matter halo in the form of actual black holes. This is speculative, and current constraints suggest primordial black holes probably don't make up most dark matter, but they could still contribute. Another angle, dark matter might help explain the seeds. If dark matter halos collapsed early in the universe, they could have triggered the formation of massive direct collapse black holes by providing deep gravitational potential wells into which large amounts of gas could fall rapidly. The dark matter wouldn't be directly accreted initially, but it would enable the formation of supermassive seed black holes by setting up the right conditions. One quirky detail: if you fell into TON 618, any dark matter particles that happened to be falling in at the same time would pass right through you without interaction on the way down, both of you heading for the event horizon together, but existing in effectively separate universes. You'd be shredded by tidal forces and vaporized by radiation. The dark matter would sail through unperturbed until crossing the event horizon and adding its mass to the black hole's total. It's oddly poetic, in a cosmic horror sort of way. Just when you thought TON 618 was comfortably sitting on its throne as one of the most massive black holes in the universe, along comes Phoenix A, or more properly the black hole at the centre of the galaxy Phoenix A, to challenge its heavyweight title. And honestly, depending on which measurements you trust and which models you use, Phoenix A might actually be heavier. This is the kind of friendly rivalry that makes astronomers argue passionately at conferences while furiously checking each other's error bars. Phoenix A's central black hole clocks in at an estimated 100 billion solar masses according to some measurements. Yes, you read that right. 100 billion with a B. That's roughly 50% more massive than TON 618, pushing it firmly into how is this even possible territory. The uncertainty on these measurements is substantial. Error bars span tens of billions of solar masses, but even the conservative estimates place Phoenix A in the same ultra-heavyweight class as TON 618. These two black holes are slugging it out for the title of most massive confirmed supermassive black hole. And depending on which paper you read this week, the winner changes. Phoenix A, the galaxy, sits about 5.8 billion light-years away, closer than TON 618, but still at cosmological distances. It's the central galaxy in a massive galaxy cluster, one of those vast structures containing hundreds of galaxies bound together by gravity. The black hole's mass was estimated by observing the dynamics of hot gas in the cluster, using X-ray observations from space telescopes. Hot gas traces out the gravitational potential, and by modelling how it flows and heats, astronomers can infer the mass of the central black hole. This method has its own uncertainties and assumptions, which is why the mass estimate comes with such large error bars. What makes Phoenix A particularly interesting is that it's not currently active as a quasar. Unlike TON 618, which we observe in its bright feeding phase, Phoenix A's black hole is relatively quiet, not accreting large amounts of matter and thus not blazing across the cosmos. This tells us something important. Supermassive black holes spend most of their lives dormant, not actively feeding. The quasar phase is spectacular but brief on cosmic timescales. TON 618 just happens to be caught during its feast years, while Phoenix A represents the post-meal quiet period. Both are probably typical supermassive black holes at different stages of activity. The discovery of multiple ultramassive black holes, TON 618, Phoenix A, and several other contenders in the tens of billion solar mass range, raises questions about whether there's an effective upper limit to black hole mass. In principle, black holes can grow indefinitely as long as they keep feeding. In practice, several mechanisms might limit their growth. Aegean feedback heats surrounding gas and prevents it from cooling and falling in. Galaxy mergers become rarer as the universe expands and galaxies move apart. The available gas supply in a galaxy centre gets exhausted as stars form, and supernova blow gas out of the galactic core. So while nothing in the physics explicitly caps black hole mass, the practical limitations of fuel supply and time might mean that 60 to 100 billion solar masses represents the upper end of what's achievable in the universe's current age. Historians still argue whether we've found the most massive black holes yet, or if there are even larger monsters lurking undiscovered in distant galaxies. Our ability to find and measure supermassive black holes depends on several factors. They need to be either active, so we can spot them as quasars, or in galaxies where we can measure gas or stellar dynamics accurately, which requires good observations. There could be dormant 100 billion solar mass black holes in galaxies we haven't surveyed carefully, hiding in plain sight simply because they're not currently feeding, and thus not drawing attention to themselves. One of the quirks of the TON 618 versus Phoenix A debate is that they're being measured by different methods, which makes direct comparison tricky. TON 618's mass comes primarily from modelling its quasar luminosity and accretion rate. Phoenix A's mass comes from gas dynamics in the surrounding galaxy cluster. Both methods have systematic uncertainties that are hard to quantify precisely. So when papers claim one is larger than the other, what they really mean is, given our current best measurements and models, we think this one might be larger, but honestly the error bars overlap and we're splitting hairs here. There are also several other contenders for the most massive title. IC1101's central black hole might rival these monsters, and there are quasars like SDS-SJ 0100 plus 2802 with black holes in the 10 billion solar mass range. As survey instruments improve and we develop better analysis techniques, the record holder for most massive confirmed black hole will probably change hands several more times over the coming decades. For now, TON 618 and Phoenix A are co-champions, both representing the extreme upper end of supermassive black hole mass, and both reminding us that the universe is capable of growing structures on scales that break our intuitive understanding. Observing TON 618 across multiple wavelengths is essential, because this cosmic monster doesn't just glow in one colour, it screams across the entire electromagnetic spectrum, from low-energy radio waves to ultra-high-energy X-rays and gamma rays. Each wavelength window gives us different information about the black hole and its surroundings, like examining a crime scene with different types of forensic tools. No single wavelength tells the complete story. Radio observations were actually how TON 618 was first discovered, back when quasars were quasi-stellar radio sources. Radio emission from quasars comes from synchrotron radiation, charged particles spiraling around magnetic field lines and emitting radiation as they accelerate. The radio emission maps out the jets and lobes extending from the quasar, structures that can span millions of light years. For TON 618, radio observations reveal extended structure around the central engine, telling us about how energy and particles are being transported outward from the black hole into the surrounding intergalactic medium. Radio telescopes like the Very Large Array and ALMA contribute to our understanding of quasars by mapping these large-scale structures with high resolution. Optical observations, visible light, show us the quasar as a bright point source, often outshining its entire host galaxy. The optical spectrum is crucial for measuring the quasar's redshift, which tells us its distance and places it in cosmic history. Spectroscopy breaks the light into its component wavelengths, revealing emission lines from ionized gases in the broad line region and narrow line region surrounding the black hole. These emission lines encode information about the gas's density, temperature, composition, and velocity. By measuring the width of the emission lines, broadened by the Doppler effect from gas moving at thousands of kilometers per second, astronomers can estimate the black hole's mass using a technique called reverberation mapping, though this works better for closer, lower mass quasars than for distant giants like TON 618. Ultraviolet observations, typically conducted from space since Earth's atmosphere absorbs most UV light, probe the hotter regions of the accretion disk. The UV emission comes primarily from the disk's innermost regions, where temperatures reach tens of thousands to millions of degrees. The Hubble Space Telescope and other UV-capable instruments have observed numerous quasars in this wavelength range, helping map the temperature structure of accretion disks. For TON 618, the UV flux contributes significantly to the total bolometric luminosity, the total energy output across all wavelengths. X-ray observations conducted by space-based observatories like Chandra, XMM Newton and NuSTAR reveal the highest energy processes occurring near the black hole. X-rays come from the corona, that extremely hot plasma hovering above the accretion disk, and from inverse Compton scattering where low-energy photons get boosted to high energies by colliding with fast-moving electrons. The X-ray spectrum shape tells us about the temperature and density of the corona, and features like the iron K-alpha emission line, a fluorescent line produced when X-rays hit iron atoms in the disk, provide diagnostics of the disk's properties and the black hole's spin. Detecting iron lines from TON 618 is challenging given its distance, but for closer active galactic nuclei, this technique provides crucial constraints. Infrared observations split the difference between optical and radio, probing dust emission and cooler gas that might be obscured in other wavelengths. Many quasars are surrounded by dusty tori, donut-shaped structures of dust and gas encircling the accretion disk. These tori absorb UV and optical light from the central engine and re-radiate it in the infrared. For TON 618, IR observations contribute to understanding the total energy budget and the distribution of material around the black hole on larger scales. Historians still argue whether multi-wavelength observations of distant quasars like TON 618 can be combined coherently, given that different wavelengths are often observed at different times, sometimes years apart. Quasars vary in brightness over timescales ranging from hours to years, so a radio observation from 2010 and an X-ray observation from 2015 might be seeing the quasar in different activity states. Astronomers try to account for this through coordinated campaigns where multiple telescopes observe the same target simultaneously across many wavelengths, but for distant objects like TON 618, getting all the desired observatories pointed at the same target at the same time is logistically difficult and expensive in terms of telescope time. One quirky aspect of multi-wavelength astronomy: different wavelength observations require completely different instrument designs. Radio telescopes are giant dishes or arrays of dishes measuring meters to kilometers across. Optical telescopes use mirrors to focus light. X-ray telescopes use grazing incidence optics because X-rays pass right through normal mirrors unless they hit at very shallow angles. Gamma-ray telescopes often don't even use mirrors, but instead detect particle showers created when gamma rays hit the atmosphere. This means studying an object across all wavelengths requires a virtual fleet of specialized observatories, many of them in space because the atmosphere blocks large swathes of the spectrum. TON 618 has been examined by this entire menagerie of instruments over decades, each adding pieces to the puzzle. The universe is teeming with supermassive black holes, millions of them, by conservative estimates, possibly billions if you count all the dormant ones hiding in galaxy centers without actively drawing attention to themselves. Nearly every substantial galaxy hosts a supermassive black hole at its core, a relationship so consistent that astronomers treat the presence of a central black hole as a standard feature of galaxy structure rather than an exception. But few approach the extreme masses of TON 618 and Phoenix A. The census of supermassive black holes spans many orders of magnitude in mass. On the lower end, some dwarf galaxies host relatively modest black holes, massing only tens of thousands of solar masses, barely supermassive and perhaps better categorized as intermediate mass black holes. The Milky Way's Sagittarius A star, at 4 million solar masses, sits comfortably in the middleweight division. Most supermassive black holes in the nearby universe weigh between 1 million and 1 billion solar masses, following a rough correlation with their host galaxy's bulge mass. The bigger the galaxy's central bulge, the more massive its black hole tends to be. This relationship, called the M-sigma relation, relating black hole mass to the velocity dispersion of stars in the galactic bulge, suggests that black holes and galaxies co-evolve. Somehow the growth of the central black hole is coupled to the formation and evolution of its host galaxy, though the mechanisms behind this coupling are still being worked out. Is it simple? More massive galaxies have deeper gravitational wells that enable larger black holes to grow? Or is there active feedback where the black hole's energy output regulates star formation and thus controls how massive the galaxy becomes? Probably both processes play roles at different times and in different environments. Ultramassive black holes like TON 618, defined loosely as those exceeding 10 billion solar masses, are rare. Astronomers have confirmed only a handful, though the exact number depends on how confident you need to be in the mass measurements before counting something as confirmed. These giants seem to reside in the most massive galaxies, often in the centers of galaxy clusters or in particularly massive elliptical galaxies that likely formed through multiple major mergers. They represent the extreme tail of the black hole mass distribution, the statistical outliers that make you double-check your data because they're so far from the typical value. One question that keeps astronomers up at night, besides the usual insomnia-inducing existential dread that comes with contemplating cosmic voids, is whether ultramassive black holes like TON 618 are rare because they're genuinely difficult to form, or if they're rare simply because we haven't finished surveying the universe yet. Current surveys are biased toward finding active quasars, which are bright and thus easy to detect. Dormant ultramassive black holes in galaxies that aren't currently merging or otherwise disturbed would be much harder to spot. We'd only find them through careful dynamical studies of their host galaxies, measuring stellar or gas velocities to infer the central mass. This is time-consuming work requiring good telescopic data, so our census of dormant ultramassive black holes is probably incomplete. Historians still argue whether the relationship between black hole mass and galaxy mass evolves over cosmic time. In the early universe, some observations suggest that black holes might have been overly massive relative to their host galaxies compared to the local universe's relationship. TON 618 could be an example of this. A black hole that grew faster than its galaxy did, at least temporarily. Later feedback mechanisms might have rebalanced things, shutting down the black hole's growth while the galaxy continued forming stars and accumulating mass until the relationship settled into the M-sigma correlation we observe locally. Detecting supermassive black holes in general breaks down into a few categories of techniques. For active black holes, quasars and other AGN, the bright emission from the accretion disk makes them easy to spot, and measuring their luminosity and spectral properties gives mass estimates. For nearby dormant black holes, you can measure the velocities of stars or gas orbiting close to the galactic center and use Kepler's laws to calculate the central mass. The Event Horizon Telescope collaboration has pushed this to the extreme by actually imaging the event horizons of Sagittarius A star and M87's black hole. Though that technique only works for the nearest supermassive black holes with large angular sizes on the sky. For distant dormant black holes, you're usually stuck inferring their existence from galaxy dynamics or gravitational lensing, neither of which provides precise mass measurements for individual black holes. One quirky fact: because supermassive black holes at galaxy centers are so common, and because galaxies merge relatively frequently over cosmic time, black hole mergers should also be relatively common. These mergers are prime sources of gravitational waves, but at wavelengths too long for ground-based detectors like LIGO to sense. Future space-based gravitational wave observatories like LISA will specialize in detecting mergers of supermassive black holes, opening a completely new window on these cosmic behemoths. When two black holes like TON 618 and Phoenix A merged, if they ever met, which they won't because they're in completely different parts of the universe, the gravitational wave signal would be detectable across the observable universe, ringing space-time like a bell with frequencies in the millihertz range. What happens inside the event horizon of TON 618 is one of the deepest mysteries in physics, and admitting that we don't know the answer is both humbling and exciting. General relativity provides equations describing space-time inside a black hole, but those equations predict their own breakdown at the singularity, the point where density becomes infinite and the curvature of space-time diverges. Whenever your theory predicts infinity, that's nature's way of saying, your math broke, go figure out better math. According to classical general relativity, the Einstein field equations without quantum corrections, the interior of a non-rotating, Schwarzschild black hole is straightforward to describe mathematically. Once you cross the event horizon, all forward time paths lead inexorably to the singularity at the centre. The singularity is a point of zero volume and infinite density, a place where the equations produce nonsensical answers. Space and time coordinates swap roles inside the event horizon in a technical sense. The radial coordinate becomes time-like, and the time coordinate becomes space-like, which is a fancy way of saying that moving toward the singularity is as inevitable as moving forward in time. You can't avoid the singularity any more than you can avoid tomorrow. For a rotating Kerr black hole, which TON 618 almost certainly is since it formed from rotating matter and has been accreting rotating material, the interior structure is more complex. The singularity becomes a ring rather than a point, a rotating circle of infinite density and zero thickness. The Kerr solution also predicts an inner event horizon and a region beyond it where the singularity is time-like rather than space-like, whatever that means geometrically. This region, if it exists, would have bizarre properties including closed time-like curves, paths through space-time that loop back on themselves, potentially allowing time travel to your own past. Most physicists suspect the inner event horizon is unstable and doesn't actually exist in nature, destroyed by quantum effects or classical instabilities before you could reach it. But the mathematics permits its existence, so we mention it while side-eyeing it suspiciously. But here's where quantum mechanics crashes the party. General relativity is a classical theory. It doesn't include quantum effects. At the scales and energies relevant near the singularity, quantum mechanics must be important. The problem is that we don't have a working theory of quantum gravity, a framework that successfully merges quantum mechanics and general relativity into a single coherent theory. String theory attempts this. Loop quantum gravity attempts it differently. Several other approaches exist, each with proponents and critics, and none yet confirmed by experiment. Without quantum gravity, we can't actually describe what happens at or near the singularity where quantum effects dominate. Some theories suggest that quantum effects prevent true singularities, perhaps replacing them with regions of extreme but finite curvature. The Planck scale, about 10 to the power of minus 35 meters, represents the length scale where space-time itself might become grainy or quantized, and below that scale our current concepts of space and time might simply not apply. The singularity might be smeared out into a Planck scale region where something else happens, something we don't have the mathematics to describe yet. Other ideas propose that the singularity is a gateway to another universe, a white hole spewing matter elsewhere, or connects to a baby universe budding off from our own. These are speculative ideas, fun to contemplate but unsupported by evidence, and difficult to test since we can't exactly peer inside a black hole's event horizon to check. Historians still argue whether information that falls into a black hole is truly lost or somehow preserved. This is the black hole information paradox, a conflict between general relativity, which says information disappears into the singularity, and quantum mechanics, which insists information must be conserved. Stephen Hawking spent decades on this problem, initially arguing that information was lost, then later conceding it might be preserved in subtle correlations in Hawking radiation. Recent ideas involve the holographic principle, which suggests that all the information about a black hole's interior is encoded on its event horizon, like a three-dimensional image stored in a two-dimensional hologram. If this is correct, then information doesn't really fall into the black hole. It gets scrambled and encoded on the surface, later emerging in the radiation as the black hole evaporates. But for TON 618, evaporation is so incredibly slow that this remains purely theoretical. One quirky aspect, from the perspective of someone falling into TON 618, the journey from event horizon to singularity would take finite proper time as measured by your own clock. For such a massive black hole, this might be several hours. During this time, you'd experience increasing tidal forces, radiation from infalling matter, and the increasingly strange geometry of space-time. Looking outward, you'd see the outside universe blue-shifted and time-dilated, potentially watching the entire future history of the cosmos play out in fast-forward. Looking inward toward the singularity, nobody knows what you'd see. Perhaps nothing. Perhaps everything. Perhaps the question doesn't make sense because the concept of seeing breaks down when space-time itself is falling apart. The singularity's nature remains one of physics' great unsolved problems. Is it a point, a ring, a region of quantum foam, a doorway to another universe, a place where the laws of physics are different? We won't know until we develop a theory of quantum gravity that makes testable predictions, and even then we might not be able to test those predictions since the interior of a black hole is causally disconnected from the outside universe. Nothing that happens inside can send signals out to tell us about it. Supermassive black holes aren't passive residents in their galaxy's centers. They're active sculptors, gardeners, and sometimes tyrants, regulating star formation and shaping galactic evolution through processes collectively called AGN feedback. The relationship between black holes and their host galaxies is intimate and bidirectional. The galaxy feeds the black hole, and the black hole dramatically influences how the galaxy evolves. TON 618, in its quasar phase, is a perfect example of a black hole actively reshaping its cosmic neighborhood. Let's start with the energy budget. Remember that TON 618 shines with the luminosity of about 140 trillion suns. That energy doesn't just radiate outward harmlessly into space, it interacts with gas in and around the galaxy, heating it, ionizing it, and sometimes blowing it out of the galaxy entirely. This is radiative feedback. The intense UV and X-ray radiation from the accretion disk heats gas clouds, increasing their pressure and preventing them from cooling and collapsing to form stars. If gas can't cool and collapse, stars don't form. The black hole essentially regulates star formation by heating the gas supply. Then there's mechanical feedback from jets and winds. Many quasars, including TON 618, produce powerful outflows, winds of gas moving at thousands of kilometers per second, and in some cases relativistic jets shooting out near light speed. These outflows carry enormous amounts of energy and momentum into the surrounding galaxy and intergalactic medium. When a jet plows into dense gas, it creates shock waves that heat the gas to millions of degrees. This hot gas can't form stars. It's too energetic, too diffuse, too disrupted. The winds can even push gas entirely out of the galaxy in a process called galactic outflow, depriving the galaxy of the raw material needed to form future generations of stars. This feedback mechanism helps explain the M-sigma relation, the correlation between black hole mass and galaxy bulge properties. As a black hole grows, it eventually becomes massive enough that its feedback energy significantly affects the galaxy. The more it feeds, the more energy it pumps into its surroundings, eventually heating gas so much that accretion slows down or stops. This self-regulating mechanism means the black hole's growth tracks the galaxy's growth. They co-evolve, with the black hole growing until it becomes powerful enough to shut down its own food supply. The final black hole mass ends up correlating with galaxy properties because both are determined by the same feedback processes. Observational evidence for AGN feedback comes from multiple sources. Astronomers observe vast bubbles of hot gas in galaxy clusters, inflated by jets from central AGN and visible in X-ray images. These bubbles can be hundreds of thousands of light-years across, containing enough energy to power 1,000 supernovae. We see high-velocity outflows in quasar spectra, gas moving at up to 10,000 kilometers per second being driven out by radiation pressure. And we observe that the most massive galaxies, which presumably host the most massive black holes, tend to have low star formation rates despite being in environments with plenty of gas. The black holes have heated the gas too much for efficient star formation. Historians still argue whether AGN feedback is primarily responsible for suppressing star formation in massive galaxies, or if other processes are equally important. Galaxy-galaxy mergers can trigger starbursts that consume available gas. Supernova feedback from massive stars can also heat and expel gas. The intracluster medium in galaxy clusters is already hot, making gas accretion difficult. Sorting out how much each process contributes is an active area of research, complicated by the fact that simulations of galaxy formation struggle to reproduce observed galaxy properties without including strong AGN feedback in their models. For TON 618 specifically, the quasar is so luminous that its radiation and outflows must be significantly affecting its host galaxy. The galaxy is probably experiencing suppressed star formation in regions where the AGN's energy has heated or expelled gas. Eventually, as the gas supply is exhausted or driven away, TON 618 will dim, the accretion will slow, and the quasar will fade into dormancy. The galaxy will then evolve more quietly, perhaps experiencing renewed star formation if gas cools and falls back in, or perhaps remaining relatively quiescent like a massive elliptical galaxy. Billions of years from now, TON 618's galaxy might look like Phoenix A's galaxy, an unremarkable massive elliptical galaxy with a dormant ultramassive black hole at its centre, quietly minding its own business. One quirky detail: AGN feedback operates on multiple scales simultaneously. On subgalactic scales, hundreds to thousands of light-years, radiation and winds heat gas in the galaxy's core. On galactic scales, tens of thousands of light-years, jets and winds drive large-scale outflows, and on cluster scales, millions of light-years, jets inflate giant bubbles in the intracluster medium, affecting the properties of the entire galaxy cluster. This multi-scale nature makes AGN feedback both powerful and complicated to model accurately. Even TON 618, this monstrous cosmic tyrant that has ruled its galaxy for billions of years, will eventually die. Not soon, not by any human understanding of soon, but given enough time, quantum mechanics ensures that all black holes evaporate through Hawking radiation, returning their mass energy to the universe in a slow fizz of particles and photons. For TON 618, enough time is a number so large it makes the current age of the universe look like a rounding error. Hawking radiation is a quantum mechanical effect discovered theoretically by Stephen Hawking in 1974. The basic idea involves quantum fluctuations near the event horizon. In quantum field theory, even empty space isn't truly empty. Particle-antiparticle pairs constantly pop into existence and annihilate each other within timescales, allowed by Heisenberg's uncertainty principle. Near a black hole's event horizon, Occasionally, one member of a virtual pair falls into the black hole while the other escapes. The escaping particle becomes real radiation, and to conserve energy, the black hole must lose mass equal to the energy of the emitted particle. Over time, this process causes the black hole to evaporate. The rate of Hawking radiation is inversely proportional to the black hole's mass. Small black holes radiate quickly. Massive black holes radiate slowly. For stellar mass black holes, the Hawking radiation temperature is absurdly cold, far colder than the cosmic microwave background, so they're actually gaining mass from absorbing CMB photons faster than they lose mass through Hawking radiation. They'll only start evaporating once the universe expands and cools enough that the CMB temperature drops below the black hole's Hawking temperature. For supermassive black holes like TON 618, the Hawking temperature is so low it's almost meaningless, around 10 to the power of minus 17 Kelvin, give or take a few orders of magnitude depending on the exact mass. How long would TON 618 take to evaporate completely? The lifetime of a black hole due to Hawking radiation scales with a cube of its mass. For TON 618, weighing 66 billion solar masses, plugging into the evaporation formula gives you a timescale of about 10 to the power of 100 years. That's a 1 followed by 100 zeros. To put this in perspective, the current universe is about 10 to the power of 10 years old. 14 billion years, a 1 followed by 10 zeros. TON 618's evaporation timescale is 10,000 trillion times longer than the current age of the universe. The universe could expand, cool, undergo heat death, have all stars burn out and all protons decay, if they do decay, and TON 618 would still be sitting there, barely warmed up in its evaporation process. The evaporation process itself wouldn't be smooth. Early on, the black hole radiates extremely slowly, emitting an occasional photon or particle over timescales longer than the age of the universe. As the black hole shrinks, it heats up. Remember, Hawking temperature increases as mass decreases. Eventually, far in the future, once TON 618 has radiated away most of its mass, the evaporation accelerates. The final stages would be dramatic. A black hole reduced to a few solar masses would be radiating significantly, glowing hot. In the final second, the remaining mass would explode in a burst of radiation, releasing energy equivalent to millions of nuclear bombs. All that mass converted to radiation, returning to the universe as pure energy. Historians still argue whether Hawking radiation is real, not in the sense of doubting the theory, which is well established, but in the sense that it's never been directly observed. Black holes astrophysicists study are far too massive and too warm relative to the CMB to emit detectable Hawking radiation. Detecting it would require finding an extremely small primordial black hole and measuring its radiation, or creating microscopic black holes in particle accelerators, which LHC cannot and will not do. It doesn't reach the necessary energies. Without direct observation, Hawking radiation remains a theoretical prediction, albeit one that most physicists accept as almost certainly correct because it follows naturally from combining quantum field theory and general relativity. One quirky implication: if black holes evaporate completely, they eventually return all their mass to the universe. This means black holes are not permanent information destroyers after all, at least not eternally. The information paradox returns here. If information is encoded in the Hawking radiation, then black hole evaporation doesn't truly lose information, just scrambles it beyond recognition. But if information isn't encoded in the radiation, then black holes evaporate and leave nothing behind, and the information is genuinely lost, violating quantum mechanics. Physicists are still working out which scenario is correct, with most betting on information conservation through mechanisms we don't fully understand yet. The ultimate fate of TON 618, then, is to slowly, imperceptibly radiate away over timescales that dwarf the current age of the universe. Long after the last stars have died, after galaxies have evaporated through stellar encounters, after protons have decayed, if they do, TON 618 will still be there, a lonely black hole in an empty, cold, dark universe. Eventually, it too will evaporate, perhaps leaving behind a final flash of radiation in the dark, witnessed by nothing and no one. It's the ultimate fate of all black holes, not to last forever, but to return their borrowed mass energy to the cosmos over timescales so long they might as well be infinite. You've journeyed with me through the cosmic vastness of TON 618, from its mind-breaking scale to its eventual evaporation in the incomprehensibly distant future, and I hope your understanding of black holes and the universe has deepened even as your eyelids have grown heavy. But more than the facts and figures, more than the physics and mathematics, there's a deeper lesson here about perspective and humility that's worth lingering on as we wind down this journey together. TON 618 is bigger than our solar system. Its event horizon could swallow everything we've ever known, our entire planetary neighbourhood, and still have room for multiple copies. It masses 66 billion times our Sun, shines brighter than 100 trillion suns, and sits so far away that its light has been travelling for over 10 billion years to reach our telescopes. These numbers stopped making intuitive sense somewhere around section 3, if we're being honest, and that's the point. The universe is not built on a human scale. It's not designed for us to grasp easily. The cosmos is vast, ancient, violent, and indifferent to whether our 8 brains can wrap themselves around its true scope. And yet, we've discovered TON 618. We've measured it, studied it across multiple wavelengths, calculated its mass and its event horizon size, understood the physics of its accretion disk and the mechanisms of its growth. We, tiny creatures on a pale blue speck of dust living for cosmic eye blinks, have reached across more than 10 billion light years with mathematics and telescopes and sheer stubborn curiosity to comprehend something that dwarfs us beyond all reason. That's the beautiful paradox of human existence. We're infinitesimally small in cosmic terms, yet we're also the universe's way of understanding itself. Every time you look at an image of TON 618's quasar glow, or read about supermassive black holes, or even just stare up at the night sky, you're participating in a grand tradition of curiosity that stretches back to the first humans who looked up and wondered what those lights were. We've come a long way from thinking stars were holes in a celestial sphere. We've discovered galaxies, quasars, black holes, cosmic expansion, the microwave background radiation, gravitational waves. We've built the Event Horizon Telescope and imaged the shadow of a black hole's event horizon. We've sent spacecraft to other planets and rovers to Mars and probes beyond the heliopause. We've done all this in the relative blink of an eye since inventing science as a systematic method of understanding reality. TON 618 doesn't care about any of this. It simply exists, feeding and radiating, governed by the impersonal laws of physics. It's not aware of us. It poses no threat. It's billions of light years away and will never affect us directly. But studying it expands our understanding of the universe, helps us answer fundamental questions about how galaxies form and evolve, how black holes grow, how the cosmos transitioned from a hot, dense state after the Big Bang to the structured universe we observe today. TON 618 is a natural laboratory, allowing us to test theories of gravity and accretion in the most extreme environments possible. Historians still argue whether the human drive to understand the cosmos is practical or purely philosophical, whether space exploration and astrophysics deserve funding when earthly problems demand attention. This debate has existed as long as space programs have, and there's no universal answer. But I'd argue that understanding our place in the universe, grasping the true scale of existence, and pushing the boundaries of knowledge are fundamental parts of what makes us human. We're a species that explores, that questions, that refuses to accept ignorance when understanding might be possible. Ton 618, and objects like it, represent the frontier of our knowledge, the edges of what we've mapped and understood. There's always more to learn, always deeper questions to ask. As you drift towards sleep, perhaps you'll dream of falling toward an event horizon, watching time dilate and the universe speed up around you. Perhaps you'll imagine the accretion disk's hellish glow, or the quiet, patient evaporation of black holes over timescales that make eternity seem brief. Or perhaps you'll simply rest, your mind processing the vastness we've explored together tonight, filing away the knowledge that the universe is stranger and larger than everyday life suggests. Remember that we live in an age of unprecedented discovery. Right now, telescopes are observing distant quasars, gravitational wave detectors are listening for black hole mergers, and scientists are analysing data that might reveal even more massive black holes than Ton 618. The story isn't finished. Our understanding of the universe continues to deepen and evolve. What we know now about black holes would astound astronomers from just 50 years ago, and what we'll know 50 years hence will likely astonish us if we could see it now. Ton 618 reminds us that the universe doesn't care about our intuitions or expectations. It's stranger than we suppose, perhaps stranger than we can suppose. But through patient observation, careful reasoning, and mathematical precision, we can understand it anyway, bit by bit, discovery by discovery. That's both humbling and empowering. We're tiny, but we're mighty. We're brief, but we're brilliant. We're insignificant on cosmic scales, but significance isn't measured in light years or solar masses. So rest now, secure in the knowledge that while Ton 618 dwarfs our solar system, and will outlast our species by incomprehensible timescales, we've nevertheless managed to reach out across the universe and measure it, understand it, and share that understanding with each other. That's not nothing. That's actually remarkable. The story of Ton 618 ends here, but the universe continues its patient unfolding, indifferent to our comprehension, yet somehow generous in revealing its secrets to those who seek them persistently enough. You've travelled far tonight, across billions of light years and through concepts that bend intuition until it snaps. That's enough for now. Let the vastness settle gently into your thoughts, not as a burden, but as a reminder that mystery and wonder persist even in an age of scientific discovery. Somewhere out there, more than 10 billion light-years distant, TON 618 continues feeding and radiating, its accretion disk blazing with the energy of trillions of suns. The light you'd see from it now, if you had a telescope powerful enough and sensitive enough, left that quasar when the universe was young, before Earth existed, before our sun ignited, before the Milky Way took its current shape. That ancient light has been travelling through expanding space all this time, crossing the vast cosmic dark, just to arrive now at our instruments and our eyes. And you, lying here in comfort and warmth, have touched that distant reality through the medium of human curiosity and scientific achievement. You've stretched your imagination across scales that evolution never prepared us to grasp, and you've done so successfully. That's worth celebrating quietly as you drift into rest. Let the numbers fade now. Let the physics equations blur into abstract patterns. Let Ton 618 recede into the general tapestry of cosmic wonders, one among countless marvels scattered across space and time. Your mind has done enough work tonight. It's earned its rest. The universe will still be here tomorrow, still vast, still strange, still waiting to be explored and understood a little more deeply. But for now, sleep. Dream peacefully, if you dream at all. And know that you've travelled farther tonight than most people travel in lifetimes.